To help illustrate some of the central ideas underlying quantum theory, we're now going to examine a realistic model that's often used to represent vibration in molecules like diatomics. So I want you to imagine two masses that are both on the x-axis and are constrained to move on the x-axis. And the first mass has mass m1, the second one has mass m2. And what we're going to be interested in doing is characterizing in a classical way the energy of these two masses. So we might start by writing down an expression that looks like this, where v1 and v2 represent their respective velocities. And those both can be related to the time dependence of their coordinates. And I'll write their coordinates as x1 and x2 here. So this is a very simple expression for the kinetic energy. Now, there's also going to be a term that relates to the energy of the interaction between the two masses. And so we'll generically write that as v, and it will be proportional to the displacement between the two. So we're going to be interested in a relative coordinates r, which is simply the distance between those two masses. And I'll draw that here. Now, if I were to rewrite this energy expression in terms of this, I'd need another coordinate as well, and it turns out that a convenient choice for that is the center of mass of this system, which could be written like this. And I'm going to take this sum of the two masses and also give that the symbol capital M. Now it turns out that I can show very simply algebraically, but I won't do it here, that in fact I could rewrite this energy now in terms of a motion, and I'm going to use capital V to represent the velocity of the center of mass, and little v to represent the velocity of the displacement between the two masses. So I could basically write this like this. All right, so I've basically converted these two terms into these two terms, where this is the motion of the center of mass, this is the motion of the two masses relative to one another. Now you notice that this interesting function of the two masses is something that we haven't seen before, and it's basically something that we call mu. And defining it explicitly here, this is something that has a special name we call the reduced mass. All right, so it is the effective mass that governs the motion of the two masses relative to one another. Now there's one last term that I haven't written here, and that is the potential function term, this term, which now is going to depend only on the one coordinate r. All right, so as we look at this expression for the energy, we can associate this term with the translation of the entire system. And we're not so interested in the translation of the entire system at this point. We're more interested in this other term, which describes the relative motion of the two masses, which we can think of as a vibrational motion. So we're going to confine our consideration now to this part of the energy expression. All right, so having written this down this way, what we're going to want to do is now relate the force that we're seeing and find a way to write that down as a potential function. Now, we haven't said anything about the force, but one of the simplest models for the force is to simply say that the force, the restoring force, is proportional to the distance between the two masses. All right, this was something that was originally proposed about 200 years ago by Hooke, so it's called Hooke's law, and it turns out that this is what gives rise to a harmonic oscillation. Whenever the two masses are pulled farther apart from one another, the negative sign in front of this pulls them back closer together. When they're drawn closer together, the negative will then push them farther apart. So it gives rise to a harmonic motion. Now we can relate the potential function to this force constant through the following relation. The potential function, if we take the negative derivative of it, that's what gives us the force. So that's equal to minus kr. Well, this gives us now a differential equation that we can solve to give us a steady form for the potential energy function, which we can write like this. So this is the potential energy function for this linear restoring force indicated by Hooke's law. Well, this is also the potential function that we associate with something called the harmonic oscillator. All right, so let's examine this a little bit and see if we can understand something about the motion of this harmonic oscillator. All right, well, we have this expression for Hooke's law for force, but we also have Newton's law of force that says force is equal to mass times acceleration. Now, in this case, the mass is the reduced mass, and the acceleration now is going to be d squared r dt squared. And this is equal to minus kr. So all I've done is equate these two expressions for the force. Hooke's law, which is the specific one for this particular model, and Newton's law, which tells us how the force varies with acceleration. But you can see that this is actually a very convenient equation that gives us an idea of how r relates to time, how r changes with time. So if I divide both sides by mu, I'll end up with an equation that looks like this. And I'm going to explicitly write r as a function of time. And this, you may note, looks a little bit like the classical wave equation that we saw sometime earlier, where we've got a second derivative of a function of time is equal to some constant, which k over mu represents a constant, times that same function of time. Now remember, in that case we used alpha as our constant, and we noted that when alpha was less than 0, that this is what gave rise to oscillatory motion. So that's what we're seeing here is oscillatory motion, because k is a force constant, which is a positive number, and mu is a reduced mass, which is a positive number. So in fact, before we used minus k squared to indicate that, I'm going to use a different symbol. I'm going to use omega squared to indicate this. But we have here a differential equation for which we can directly write down a solution because we've seen it before. And in fact, I'm going to write that solution now as a cosine omega t plus b sine omega t. And omega now is the vibrational frequency that this particular system would have. So in essence, what we've done is we've gone through and taken two independent masses, hypothesized a restoring force that's a linear restoring force due to Hooke's law to it, and that has enabled us to actually get a solution for the behavior of those two masses relative to one another using Hooke's law and the harmonic oscillator potential. Now, one last thing that I would like to point out here, the way I've defined k and mu and omega is such that I can rewrite this force constant as the reduced mass times the harmonic oscillation frequency squared. All right, so this gives us a way to rewrite our total energy. Our total energy, remember, was just written up here as 1/2 mu times v squared plus the potential. Well, now the potential is given by this can be written as 1/2 mu omega squared r squared. This is a v. Make that clear. All right, so what this is describing now is the classical motion of an oscillator, classical motion of a mass that is in a potential function that looks like a parabola. Okay, whenever we have y equals x squared, that is a parabola. And I show you a picture of this on the next page. This is a picture of what a harmonic oscillator potential function looks like. So I can label this function as v of r. This really should be an r down here. And so you can see it's a potential function, and the system is going to be like a ball that's rolling around inside a bowl of this shape. So it's going to roll back and forth over time. Now at a particular energy E, we find that there are specific points at which this oscillator reverses course. So if this was the energy of the oscillator, these would be the points at which it turns back and goes the other way. Well, we call these the turning points. and they are simply given by the places where the total energy is equal to the potential energy, and we solve for r. So in other words, energy equal to 1/2 k r squared, or 1/2 mu omega squared r squared. And if I solve for r, I'll end up with r is plus or minus the square root of 2e over mu omega squared. So we can find what the positions of those turning points are. This is a purely classical phenomenon because, as we'll see presently, when we get to quantum wave functions, they don't, strictly speaking, obey those turning points, but they have a different sort of behavior when they reach something near those turning points, something for a future video.